Welcome to ES 310 Lesson 31. Today we will be reviewing the impulse momentum and conservation of momentum methods that we've looked at in the last couple of lessons by looking at a few more examples of each. To review the rigid body impulse momentum equations, we have that the linear momentum in the x and the y directions plus the impulses in the corresponding directions is equal to the final linear momentum in each of those directions. We also have that the rotational momentum around the center of gravity plus the impulse, which is the integral of the moments over a differential time element, is equal to the final rotational momentum around the center of gravity. We can also sum moments around any instantaneous center of zero velocity that might be present in our problem. Our first example is somewhat more complicated than the ones we've seen thus far because it involves two bodies that are pinned together at this joint B that are rotating in a joint fashion. So let's draw Freebody diagrams of each of these two bodies. We have the left-hand bar and the right-hand bar. The right-hand bar is the one with the impulse on it. So the impulse is already force times time. This is 45 degrees. We'll remind ourselves of positive directions. That's the positive x. This is the positive y. And at the pin, we'll draw positive forces on the right-hand side because we don't know the directions of the forces at the pin. So we'll draw a positive bx and a positive by. Then on the left-hand side bar, we're going to have equal and opposite forces. So we've got a negative bx and a negative by. And those are the only forces acting on these because this is in the horizontal plane, so gravity does not play a role. We will call this bar G right and this bar G left. And now we can write the impulse momentum equations for these two bars. So we'll start with the left bar and then we'll do the right bar. So in the x direction, the left bar, we have the initial linear momentum, mv left x direction 1, plus the impulse in the x direction, which is due to bx, and that's a negative bx times time, is equal to the linear momentum left in the x 2. The y direction, we have a similar equation, mv left y1 plus by is also negative times t is equal to mv left y2. In rotational, that's our positive rotation direction, we have a moment of inertia around g times omega 1 left 1 plus the moment is going to be caused by by. Bx goes through the point, so by times L over 2, half the length, and that's a negative moment times t, is equal to Ig omega left 2. Now the initials are all going to be 0 because because it's starting at rest. So we have this is 0. This one is 0, and this one is 0. Alright, let's write the similar equations for the second bar, the right bar. We have mass velocity of the right in the x direction 1. And then our impulse here, we have bx, which is positive bx times t. And we have negative I cosine of 45 because it's pointing to the left. So this total then is our total impulse is equal to mass times the velocity of the right in the x direction 2. Similarly for the left, we have mass times the velocity of the right in the y direction 1 plus byt, and then the I is in the positive direction for the y, so plus I sine of 45 is equal to mv right y2. And rotational, this is ig right, and these are ig lefts. So ig right, omega right 1, plus the moment, the only force that's going to cause a moment around point G is the by, because I and bx go through that point. So we get by times L over 2, that's a negative moment, times time, is equal to IGR omega R2. Once again, all the initial ones are 0. So currently, let's list out our unknowns. We'll start writing them across the bottom of the page here. We do not know what bx is. We do not know what by is. We do not know what the velocity of the left-hand bar in the x direction final is. We do not know what the velocity of the left-hand bar in the y direction final is. We do not know what the velocity of the right-hand bar in the x direction final is, or the velocity of the right-hand bar in the y direction final. And we do not know what omega left final is or omega right final is. So far we have 1, 2, 3, 4, 5, 6, 7, 8 unknowns, but you only have 6 equations. So we need some equations that are going to relate some more of these unknowns. And those equations are going to be our kinematic velocity equations, right? Because these bars are joined together, their velocities should be based on each other, connected in some way. So we can write the velocity of the center of mass of the left-hand bar as equal to the velocity of point B plus omega crossed with the position of the center of gravity of the left-hand bar with respect to B. So that's one equation. We have a similar equation for the right-hand bar. Velocity of the center of mass of the right-hand bar is equal to the velocity of B plus omega of the right-hand bar, these are left-hand bar, crossed with R of GR crossed with B, from B. Right, these are vector equations, so we can write out 2 equations for each of those. We have the I hat part, which will be V of LX2 is equal to VB VB x2 plus omega, positive omega crossed with GLBR, so it's the position of GL relative to B, so that's a negative R, so positive J into negative I gives us negative J. So there is no I component from this term. In the J term, then we have that VLY2 is equal to VBY2 minus the R is L over 2, omega L. Then on this side, we have V right x2 is equal to VB x2. And V left x y2 is equal to VBY2 plus L over 2 omega R. Because in this case we've got a positive omega crossed into an R in the positive I hat direction, which gives us positive J hat. Alright, so we have introduced 2 more unknowns, which are VBX2 and VBY2, but we've introduced 4 new equations. So we now have 10 equations and 10 unknowns, which may not be easy to solve, but is possible to solve. But we'll stop at that point. Now let's take another example of a problem which will involve general planar motion of a rigid body. but that is short enough for us to actually solve all the way through. So we have a slender rod, and it has a mass of m acting at its center of mass g. It's hung by its end on a cord. And initially it's at rest, and then it's hit at the bottom with an impulse I, and we need to figure out the location of this point P around which the rod appears to rotate. So if the rod is rotating around point P is going to be an instantaneous center of zero velocity. So let's write out, we only have two directions here. We've got the x direction and we've got the rotational direction. Nothing interesting is happening in the y direction. So we'll do the x equation, which in this case is the linear momentum of the center of mass in the x direction, initial, plus the force, the impulse in the x direction, which is just I, which is already F times t, is equal to the mass times the velocity of the center of mass in the x direction 2. It started at rest, so this is equal to 0. Then we do our moment equations, or rotational equations, and we have I around center of mass times omega 1 plus the impulse, the force impulse, which is I, times a distance from G to the end, so this is L over 2. So this is L over 2 is our distance to get our moment. It's a positive moment, so that's going to be a positive rotational impulse, is equal to Ig omega 2. So from the top equation, we know that I is equal to mvgx2. So we can plug that in to this equation. That's also 0. So we get that L over 2 times mvgx2 is equal to Ig omega 2. Now we need to relate this velocity to this omega. So since point P is the instantaneous center, we can write our velocities relative to that. So our velocity of point G is equal to our velocity of the instantaneous center, plus omega crossed with r of point G related to IC. And IC is point P, so this is going to be 0. Vg at this initial point right after impact is only in the x direction. So this is Vg x, and it's after the impulse, so 2, is equal to omega is in the k direction crossed with r gic in the y direction, or the j hat direction, and that distance is from G to P. Actually, it's from P to G, right? Position of G relative to P. So that is going to be omega times, what is this distance? This is y minus L over 2 is the distance. And sign-wise, we've got a positive omega crossed into a negative j, gives us a positive x. Alright, so now we've related the v to omega. This is omega 2 after impulse. We have two equations in omega and v. We are trying to solve for y. So let's take this equation, plug it in over here. We get L over 2 times mass times omega 2 times y minus L over 2 is equal to, and here we get Ig for a rod rotating around its center is 1/12 of ml squared times omega 2. Alright, so there's an m on both sides, they cancel. There's an omega on both sides, they cancel. There's an L on both sides, they cancel. And so now we get 1/2 of y minus 1/4 of L is equal to 1/12 of L. Move L over to the other side. We get 1/4 plus 1/12, so that's 3/12 plus 1/12 is 4/12, which is 1/3. So 1/2 of y is equal to 1/3 of L, or y is equal to 2/3 of L, which is our final answer. To review conservation of momentum, and this occurs when all of the impulses are zero. So either there are no significant forces, or those forces act through the center of mass, in which case the linear would not be conserved, but the rotational would be conserved. When we don't have these impulses, all of our forces are non-impulsive, then we can say that the linear momentum initially is equal to the linear momentum after the impact, and we could have two of these equations, one in the x and one in the y direction. And then rotationally, the angular momentum before impact is equal to the angular momentum after impact. If you remember back to what we did in linear conservation of momentum, we also had a coefficient of restitution. And that coefficient of restitution still holds here. The velocity of A after impact minus the velocity of B after impact divided by the velocity of B before minus the velocity of A before is equal to our coefficient of restitution. And so if we know the coefficient of restitution, we can handle solving for two unknowns. Whereas if we don't know the coefficient of restitution, we can only solve for one. So let's take a look at an example of conservation of momentum. We're looking at a rotating system where one part of that rotating system leaves it with a linear velocity. This is a similar type of problem. You also often see something coming in with a linear velocity. The key is that the velocity of the piece that is leaving, in this case the man, is given in term as a relative velocity to the rotating system. And so that's what's new in this example, is this relative velocity. So in our case, we have a 150-pound man. He's standing on a platform. He jumps off the platform, and the platform starts to move as he starts to move. His relative velocity is 5 feet. So if we remember the definition of relative velocity, it says that the velocity of a man is equal to the velocity of the platform plus the relative velocity of the man relative to the platform. Okay, so in our case then, the velocity of the platform is going to be an angular velocity. So he jumps from this point. So how do we write the speed of that point, Vp, in terms of the angular velocity? Well, first of all, if the man jumps off that way, this platform is going to start to turn that way. So that's omega. So Vp then is going to be negative, and it's going to be r omega, plus Vmp is 5, which is positive. And r is this distance from the center to where the man is, which is 8. So Vm is going to be negative 8 omega plus 5. So let's leave that for a second, and let's look at our conservation of momentum equations. We're going to use the conservation of angular momentum. So h around the center of mass, which is also a stationary point, is equal to HO2. Initially, everything's at rest, so this is going to be 0, but I want to write out the expression regardless. So initially we have the rotation of the platform giving us angular momentum, plus the rotation of the man, who acts like a particle moving in a circle around the center. And so the angular momentum for that particle moving around in a circle is equal to the mass times r squared times omega. And those two omegas are the same. In this case, those two omegas are 0, so this is going to be equal to 0. HO2 has the angular momentum of the platform, which in our case is negative because omega is negative. We get negative I naught omega. And then we have the angular momentum of the linearly moving particle, right? It's no longer moving in a circle. And so its angular momentum is mv, which is its linear momentum, times r. I naught is the moment of inertia of this platform, which they tell us should be treated as a circular disk. So we can look that up, and the angular momentum is 1/2 of the mass of the disk, r, times the radius of the disk squared. So in our case, this is 1/2 of 300 over 32.2 times 10 squared. Alright, so now if we plug some numbers in, we have this side of the equation is equal to 0, and then we have negative 1/2 300 over 32.2 times 10 squared times omega, which is what we're trying to find, plus the mass of the man, which is 150 over 32.2, times the velocity of the man, which is negative 8 omega plus 5, times the radius of where the man is, which is 8. So we have one equation with the only unknown being omega, so we can solve for that, and we will get an omega equal to 0.244 radians per second. So the key here is before he jumps off, if this was spinning, the man would be moving like a particle moving in a circle. So this is the I for a particle, mr squared, times omega, which would be its rotational inertia. After he jumps off, he's now a particle moving linearly that has a rotational momentum from the linear momentum times r. So that's the key difference there between the before and the after. Alright, our final example, example 4, we're going to use this coefficient of restitution. So we have a ball that comes in, it hits a stationary bar at a distance d down from its pin, and we need to figure out what is our omega after impact. So if we're looking at a conservation of momentum, we have the angular momentum before is equal to the angular momentum afterwards. We're going to pick point A, which is our stationary point. So I'll change those to A. And so we can write this out. Initially, the bar is not moving, so the IA omega 1 would be 0. The ball is moving, and it's a linear momentum that is happening at a distance d down, which is then equal to, afterwards it is spinning, so we do have an I omega 2, and then the ball bounces off and goes in probably the other direction, but we're not sure of that, so we'll just assume positive direction, which will be mv ball 2, this was b ball 1, times still the same distance d. Alright, so IA, we can find that, is a rod pinned at one end, so that's 1/3 of ml squared, which in our case is 1/3. The mass is 6 over 32.2, and the length is 3 squared, which gives us 0.559. So we have one equation, but we don't know omega 2 or VB2. So we have two unknowns, one equation, we need another equation. So our equation is going to be the coefficient of restitution equation, which says that the velocity of the ball 2 minus the velocity of this beam 2 that's hitting at C, so I'll call that C, divided by, this is 2, VC1 minus VB1. So VC1 is going to be 0. We need to relate VC2 to omega 2, and so if we look at that, it's rotating around a stationary point, so VC2 is going to equal distance d times omega. So VC2 then is D times omega, and omega, this is omega 2. And so now we're down to 3 equations, 3 unknowns. So let's plug some of these in. We have here 1 pound times the initial velocity of the ball, which is 50, times the distance, which is 2, is equal to IA, so 0.559, times omega 2, which is the velocity VC2 divided by distance 2, plus 1 over 32.2 times VB2, which we don't know, times 2. So we can rewrite this as a single expression in terms of VC and VB. Here we have another single expression in terms of VB and VC, because this is equal to 50. And we can solve those two equations and we will get VC equal to 15.45 and VB2 equal to negative 19.5. So we were right, the ball does bounce back and go back the other direction. And if we wanted to find omega, we just use this expression. So omega is equal to 15.45 divided by 2, which is equal to 7.725.